Hey everyone, welcome back. Today we're embarking on a pretty fascinating journey right into the fundamental building blocks of our universe. We're going to be exploring KSSM Science Form 1 Chapter 5, which is all about matter. We'll start out by looking at the big, macro objects we interact with every single day, and then we're going to zoom all the way down into the invisible micro world of particles that makes the whole shebang possible.
Okay, let's dive right into this with a quick thought experiment. Is an invisible breeze considered matter? Think about it. When you stand outside and feel the wind on your face, you can't actually see it, you can't grab it, but it's undoubtedly there, right? So does something so invisible and intangible follow the exact same physical rules as, say, a heavy rock or a flowing river? Hold on to your answer, because we're going to solve that puzzle in just a minute.
Here's our highly structured roadmap for today's explainer. 1. What is matter? 2. Properties and classification. 3. The 3 states of matter. 4. Changes of state. And finally, 5. Summary and revision.
All right, Section 1. What exactly is matter?
This right here is the critical foundation for literally everything else we'll discuss today. The golden rule of science is beautifully simple. Matter is defined as anything that has mass and occupies space. That's it. Almost everything in nature is matter. Living things, like humans, trees, and animals, yep, they have mass and take up space, so they're matter. Non-living things, like water, soil, and rocks, also matter. And to answer our earlier question, yes, air is also matter. Even though you can't see a breeze, air absolutely has mass and it occupies space. Therefore, that invisible wind on your face is for sure matter. On the flip side, things like light, sound, and heat, well, they're non-matter, simply because they don't have mass or take up any physical space.
Moving right along to Section 2, Properties and Classification.
So, since almost everything around us is matter, how do scientists actually tell all these different materials apart in nature? Well, they do it by looking at 2 distinct sets of hidden rules: physical properties and chemical properties. Physical properties are characteristics we can identify using our 5 senses, or basic measuring tools. This includes things like a material's melting point, boiling point, or whether it dissolves in water. Importantly, observing a physical property doesn't create a new substance. Chemical properties, on the other hand, only become evident when a substance reacts and changes into a completely new substance, like flammability. The original composition is fundamentally altered.
And this brilliantly illustrates the difference. Notice how ice melting into water is just a physical change based on a physical property, its melting point. The ice turns to liquid, but it's still H2O, it's still water. No new substance is formed there. But compare that to a rusting bicycle wheel. When iron is exposed to water and air, rusting occurs. Rusting is a chemical property. The iron reacts and forms a completely new substance with a totally different composition from the original iron. It's a permanent chemical change.
Now, a really cool physical property used to classify matter is density. Density is basically just the mass per unit volume of a material. It's what determines if something will float or sink in water. Notice how the oil sits beautifully in a layer right on top of the water. Why does it do that? Because oil has a lower density than water, which causes it to float. If we dropped a heavy glass marble in there, it would sink straight down to the bottom because it has a higher density.
We can also classify materials by their melting and boiling points, or by their solubility. Solubility is just the ability of a substance, which we call the solute, to dissolve into a solvent to form a solution. It's incredibly relatable. Think about making a cup of morning coffee. When you stir sugar crystals into the hot coffee, the sugar is the solute dissolving into the coffee, which acts as the solvent. Different substances have different solubilities, which makes it a fantastic, everyday way to classify the materials around us.
Okay, Section 3, the 3 states of matter.
This is where we shift gears from the macro world, the stuff we can easily see and touch, into the micro world of invisible rules. To truly understand the states of matter, we have to grasp the kinetic theory of matter. This theory tells us that matter is made up of tiny, discrete particles that are constantly moving. These particles are so unbelievably small we can't see them with the naked eye, or even a regular light microscope. You'd need a highly advanced electron microscope. But the big takeaway here is that absolutely nothing in the physical world is truly sitting perfectly still. Everything, everywhere, is vibrating or moving at the microscopic level.
Let's see how this builds our 3 states of matter: solid, liquid, and gas. In a solid, like the wood or iron used to build bridges, particles are packed very closely together. They basically just vibrate in a fixed position, kind of like people packed tightly into a crowded stadium. Because of this arrangement, solids have a fixed shape, a fixed volume, and are totally incompressible. In a liquid, the particles are still close, but they're arranged loosely, moving freely and colliding with each other. Liquids have a fixed volume, but they take the shape of whatever container you pour them into, and they're very difficult to compress. Finally, gases. Gas particles are spaced incredibly far apart, moving randomly and super fast in all directions, like kids running wildly across an open sports field. Gases take both the shape and volume of their container and are highly compressible.
Now, because particles are constantly moving, they undergo a pretty neat process called diffusion. Diffusion is when particles of a substance naturally move from an area of high concentration over to an area of low concentration. Have you ever wondered why a quick spray of perfume can be detected from all the way across a room? It's because those small perfume particles travel randomly alongside the air particles, spreading out to fill the space. And because gas particles have so much empty space and move so rapidly, the diffusion rate is highest in gases. It's a little lower in liquids and incredibly slow in solids.
All right, Section 4, Changes of State. So we know the 3 states, but how exactly does matter morph from one state to another? The secret ingredient here is heat. When heat is supplied and absorbed by a substance, it gives those tiny particles way more kinetic energy. They start vibrating faster and faster. If you heat a solid, it absorbs heat until the particles literally overcome the force of attraction holding them together, breaking free to become a liquid. We call this melting. If you keep heating that liquid, the particles gain even more energy, eventually moving totally freely as a gas. This is boiling or evaporation. And in some special cases, a solid absorbs heat and turns directly into a gas, just skipping the liquid phase entirely, a really cool process called sublimation.
Now, the exact opposite happens when matter is cooled down, meaning heat is released. When a gas cools, its particles lose kinetic energy. They slow down and move much closer to one another, turning back into a liquid. This is condensation. If you continue to cool that liquid, releasing even more heat, the particles lose so much energy that they get locked back into a fixed, vibrating position. The liquid turns into a solid, and we call this freezing.
So here is the absolutely crucial point, and definitely pay close attention to this if you're prepping for exams. During these actual changes of state, like when water is actively boiling or ice is actively melting, the temperature remains absolutely constant. If you stick a thermometer in boiling water, it stays right at 100 degrees Celsius until all the liquid turns to gas. Why? Because the heat energy being supplied is used entirely to overcome the forces of attraction between the particles, not to raise the temperature. And as a bonus fact, the overall mass remains perfectly constant throughout these changes too.
And that brings us to Section 5, Summary and Revision. Let's do a quick recap. We have covered a ton of ground today, from the macro right down to the micro. Here is your rapid-fire summary. Remember, matter is literally everything that has mass and occupies space. We understand matter through its physical properties, like melting point, and its chemical properties, like rusting. We can classify materials based on their density, boiling point, and solubility. Underneath it all is the kinetic theory of matter, tiny, discrete, constantly moving particles that arrange differently to give us solids, liquids, and gases. And finally, matter changes states by either absorbing heat to break particle bonds or releasing heat to bring those particles closer together.
All right, now I want to challenge you a bit. Pause the explainer if you need to and test your knowledge with these 3 revision questions. First, can you differentiate physical and chemical properties? Remember, one creates a new substance, the other doesn't. Second, why does the smell of cooking spread across a house? Think back to the process of diffusion in gases. And third, why is temperature constant during the boiling of water? Hint, think about what that heat energy is actually being used for at that exact moment.
If you found zooming into the particle level fascinating today, you are going to love what's coming up next time. In Chapter 6, we're tackling the periodic table. We're going to zoom in even further to look at atoms. Just to give you a quick preview of how incredibly small an atom is, imagine an orange. If you enlarge that single orange to the size of the entire Earth, that is the scale we're dealing with when looking at atoms under an electron microscope. It's literally mind-blowing.
But before we wrap up this explainer, I want to leave you with one final, kind of profound thought to ponder. We just learned that solids, liquids, and gases are all made of discrete, moving particles with spaces between them. So, if absolutely everything physical in the universe is made of these moving particles of matter, what exactly is all that empty space between them made of? Think about that for a while. Thank you so much for joining me today, and keep exploring.